Okay, thank you. So, very good morning to all, and thank you for the invitations to deliver a talk on quality-aware ECG PPG signal processing techniques for energy-efficient, trustworthy health monitoring. The main objective of today's presentation is to reduce the false alarms, latency, improve the energy efficiency by exploring the lightweight signal processing techniques for the analysis of ECG and PPG signals. So, if you see the major application of any health automation technologies, which includes control and monitoring, and in the monitorings, we like to see event detections, classifications, and predictions by exploring advancements in the sensors, Internet of Things, signal processing, and deep learning architectures, with the objective of reducing latency and improving the energy efficiency and the reliability of the health monitoring devices. So, if you see various kinds of biomedical signals which are sensed from the human body, those signals will be extensively used for physiological monitoring, fitness monitoring, and mental state monitoring by using either wearable devices or portable devices. So now we like to know what are the different kinds of wearable devices that will be used for sensing biomedical signals and their limitations. If I use wrist-worn devices, which is called smartwatches, which can produce a ECG and PPG signal by using a dry electrodes, or we can say metal contact electrodes. But when we check the quality of the signals by using these two electrodes, which will be very poor as compared to the signal which will be sensed by using wet electrodes. That is the one major objectives or aim to know what type of electrodes that will be used for sensing ECG signals. So if it is a dry electrodes, we will have a poor quality signals as compared to the ECG signal that is acquired or collected by using wet electrodes. Now, the wet electrode has many advantages in terms of producing a good quality signal, but the disadvantage is it's not more compatible for the users because we should always apply a gel, and that is also will be a challenge in the case of a continuous health monitoring devices. So therefore, we like to use a dry electrode to sense the ECG signal, but it will have a poor quality signal. So therefore, we need to check the quality of the signal before extracting the vital sign parameters so that we can ensure the trustworthiness of the vital sign monitoring systems. So now all these biological signals, particularly ECG and PPG, will be used to extract various kinds of physiological parameters, including heart rate, which is known as a pulse rate, respiration rate, blood pressure, SpO2, blood glucose level. In addition to that, we will also measure body temperature, bilirubin level, skin conductance level for physiological monitoring applications. So we will also use a set of parameters to monitor the fitness, that's called energy expenditure, step counter, daily activity indicators. We will also use ECG and PPG to recognize the mental state of the individual, which is called emotion and body feelings and thought process. Now, we can use ECG and PPG, extract the respiration rate, because the ECG and PPG will undergoes for respiratory modulations. That means we can see amplitude modulation, baseline modulations, and frequency modulations in either ECG and PPG. By extracting these modulating features, we can measure the respiration rate from the ECG and PPG without using any additional sensor. So that is one of the advantage of using ECG and PPG. That means without additional sensor, without use of additional sensor, we can extract the respiration rate from ECG and PPG if we can understand the respiratory induced modulations, which includes amplitude modulation, baseline modulation, and frequency modulation. But that modulations can be accurate, or we can say the waveform will be more accurate if the signal is free from noises or noises and artifacts. But it will be challenging under ambulatory conditions and exercise conditions. These two signals will be corrupted with various kinds of noises. And we can also use PPG to measure the blood pressure, which is called a cupless blood pressure estimation. We can also use ECG and PPG to measure the blood pressure, which is also known as a cupless blood pressure, which is very much useful for ambulatory blood pressure monitoring applications. We can use PPG to measure the SpO2. We can use ECG and PPG to measure the blood glucose level non-invasively. So these are the main advantages, or we can say application of ECG and PPG. But we use different kinds of electrodes, and also we'll sense these two signals in a different recording conditions. So one is called resting condition, ambulatory conditions, and exercise conditions. So the movement of the electrodes induces noises and artifacts that can be very severe or often or frequently in a ambulatory and exercise conditions. So therefore, checking the quality of the signal is most important. Therefore, my presentation is today quality of our ECG and PPG signal processing techniques to create or develop a trustworthy vital sign monitoring systems. So now, what are the different kinds of sensing node that will be used for collecting these type of biomedical signals? So why do you want to know? Which is most important to know to understand what type of clinical information that can be seen if I follow implant sensing node, if I use a body surface sensing node, if I use contactless sensing node. And also, what are the noises and artifacts that can be seen if I go with the implant sensing node, body surface sensing node, and contactless sensing node. In addition to that, what are the challenging problems that need to be addressed if my sensor is implanted sensor? How do you energize them? How do you communicate with them? Then if it is a body surface, what are the other challenges in terms of noises and artifacts? So therefore, we must highlight what type of sensing node that will be used for our specific applications. So it will be implant sensing node. It has different kinds of challenges and applications. If it is a body surface sensing node, it will have a different type of noises and artifacts with a different application and clinical information. Then if it is a contactless, we use a camera to sense a pulsatile waveform to measure the pulse rate. But the same pulsatile waveform cannot provide other important features like dichrotic notch that will speak more accurately, maybe will not be more prominent, but as compared to the fingertip PPG, which is called a contact-based sensor. So therefore, we must know that yes, if I'm going to use contactless, then it will have some specific features, not all important prominent feature, which will be used for diagnostic applications. So this is most important slide that yes, I'm going to use implant sensing node, then the challenges and the clinical information will be different. But I'm going to use body surface, the challenges and the clinical information will be different. Now, this is the most important slide. So as an example of signals everywhere from the human body, we can sense it by using various kinds of contact and non-contact sensors. So sometimes we can say what is called bioelectric signals, bioacoustic signal, biothermal signals, biomagnetic signals, we can say particularly that's called myosignals. That means bioelectrical signal, bioacoustic signal, biochemical signal, biothermal signals. So now by using all these signals, we can develop health and fitness monitoring systems. Now, why do you want to know all these parameters and its ranges, which is most important for today research work? It's not that just knowing the deep learning networks and having a database or downloading the database, using some libraries of Python for a deep learning, developing some systems, we cannot create an innovative system in terms of improving the energy efficiency and addressing the reliability under a different kinds of noises and artifacts. So therefore, we must know what are the different kinds of vital signs that will be extracted from the ECG and PPG and what will be their ranges. And this is the slide. It shows the normal range of heart rate, respiration rate, blood pressure, oxygens, and body temperatures. In addition to the normal ranges of each of these vitals and parameter, we must know the complete, or you can say the heart rate range for a human, respiration rate for a human, blood pressure range for a human, and blood oxygen range for a human, then body temperature for a human. Let's take a heart rate, which varies from 60 to 100 beats per minute in the case of a normal under resting conditions. It's not applicable for sportsmen or children. It's a specific adult. And resting conditions, we define the normal heart rate is 60 to 100 beats per minute. This information is very important. Under resting conditions, for adult, we are defining 60 to 100 beats per minute, but it can go below 60 for the sportsman as a normal range. It will go above 60 for the case of a children or an infant. So therefore, we must know what will be the normal range under resting conditions, ambulatory conditions, or exercise conditions for a sports athletic persons or a normal persons and a children. Now, if I take a heart rate range for a human, it will be 30 to 300 beats per minute. If you see any kinds of bedside monitoring, you will find this range 30 to 300 beats per minutes. Within that, we have normal range and abnormal range. If it is below, if the heart rate is below 60 beats per minute, it is called bradycardia. If the heart rate is above, let's take 120 beats per minute, okay, then we can say completely it's a tachycardia. But if you look at the heart rate range, it's a 30 to 300 beats per minute, which is the most important information to develop a energy efficient pulse rate estimation techniques. So instead of choosing a sampling rate, what is called very high rate, for example, 100 samples per second to measure the pulse rate, I can choose a lower sampling rate to measure the pulse rate by knowing the pulse rate frequency range. The pulse rate frequency range is for this case is 0.5 hertz to 5 hertz. So therefore, I can design a PPG sensor with a sampling rate of 25 samples per second to collect the PPG signal, which is sufficient to estimate the pulse rate from the what is called low rate PPG signal instead of having a PPG with 100 samples per second, which consumes more energy, and it will also it will also increase the computational time. So therefore, we must remember all these specific parameters so that we can fine tune the sensing module and signal processing module to improve the energy efficiency by reducing the overall energy consumption. That means if I'm able to get the pulse rate accurately for the PPG signal with the sampling rate of 25 samples per second, then I can save one fourth of this. What is called, we can say 75% of the energy if I sampled at a rate of 100 samples per second. So that is the main advantage of, or we can say, significance of knowing all these ranges of the pulse rate and heart rate. One can argue, I will not remember, I will not study all these parameters, but I can give to a deep learning, it can develop, it can produce a pulse rate, or you can say it can estimate the pulse rate from the PPG signal. It can do, but it will not be it cannot be a energy efficient techniques. The energy is most important. And also the model size is very high. It will consume more energy and it demands high computational hardware. So to estimate one pulse rate using a edge platform, it may not be a more effective solution, and the cost also very high, and it also consumes the more. So therefore, we must remember the ranges of these vital sign parameters, particularly heart rate, respiration rate, and blood pressure, oxygen saturation, body temperature. Now, if this slide summarize that, yes, I have a wrist-worn device, body-worn device, smartphone, IoT based, and computer-aided diagnostic system. That means I can compute or I can measure the pulse rate at the edge level, at the device level, at the cloud level. So that's called edge computing, cloud computing. And then we have advantages of edge computing as compared to cloud computing, including user privacy, security, low latency, communication failure, network coverage, bandwidth utilization cost, mobile network utilization cost, and treatment cost and battery life. These are the advantages of edge computing as compared to cloud computing. So that is one of the advantages, the privacy and the communications. We have to ensure the communications when we do the pulse rate estimation at the cloud. But I can do the pulse rate estimation at the edge or at the device, and it can be a very good intelligence to the individual, and they can know what is the pulse rate immediately. Otherwise, we have to wait. We have to transmit the signal to the cloud. The cloud has some traffic load, and then it will be computed or it will be measured, and that measure will be again transmitted to the wristwatch. It will take some kind of transmission delay or latency. So these are the main advantages of edge computing as compared to the cloud computing. Now, in addition to that, we must always check the quality of the signal, because the PPG is sensed by using a optical technology that will operate in a transmittance mode and reflectance mode. So each of these modes, or we can say sensing mode, will have a own advantages and disadvantages. So we will have, let's take I have a reflectance mode, then the noise will be more. Now in such a cases, we need to check the quality of the signal to accurately measure the pulse rate. Otherwise, the noise can introduce some kind of a pulse rate. That pulse rate may be a normal or abnormal due to the noises. So that can increase the false alarms. That maybe the false alarms due to the inaccurate measurement of the parameters. So now the frequent false alarm is so annoying or disturbance to the medical professionals, or we can say AI. So therefore, we need to check the quality of the signal before extracting any kind of vital sign parameters, or before performing emotional recognitions, biometric authentications, or any kind of cardiovascular disease prediction. Otherwise, we will have more false alarm. So that's the main contribution of our research work, that how to check the quality of the signals in an efficient manner. That means by exploring a lightweight signal processing technique to check the quality of the ECG and PPG signal. Now, in addition to that, we can accurately measure the pulse rate, and we will transmit that pulse rate to the cloud, or we can say to the doctor, or to the diagnostic center, or to the AI platform. Today we are what is called highly influenced by AI, because everyone is talking about AI. But also one of the example where AI cannot do anything also, because we cannot able to collect all the information which is required for the AI platform. Let's take your wristwatch, okay, or I'm wearing the wristwatch, where the wristwatch is very good to accurately measure the pulse rate. Now the pulse rate is given to the doctor for the diagnosis purpose. I'm able to accurately estimate. Now once we estimate the pulse rate accurately, we are transmitting to the, or we are sharing with the doctor, or we are sending to the AI platform to understand my health info or health risk factors. Now, when I send a pulse rate of, for example, 120 beats per minute, it becomes abnormal. Let's take 125 beats per minute. It becomes abnormal. But the abnormality in a pulse rate can be seen. That means abnormality in terms of the value, it's a 125 beats per minute. The same 125 beats per minute, we can see for a subject under running conditions. If any subject is, or individual or user is running, his heart rate will be very high. It will be more than 120 beats per minute. Now, this 125 beats per minute can be correlated with the physical activity of a person, or can be correlated with the defects of the heart function or malfunctioning of the heart. Now, the same 120 can be seen for a subject with the emotions. If there is a excitement, his heart rate is very high, or the same person is sleeping and the heart rate will be very low. So that means very low heart rate. We cannot say that heart rate is, it's related to the pathological cases of the bradycardia, or the pathological cases of the tachycardia if we have high heart rate. It needs contextual information. Is it audible what I'm speaking? Hello?
Yes, sir. Yes, sir. Audible, sir.
Yes, sir. Yes, sir.
Now, if I'm not embedding this physical activity information, emotional information, and weather information, because the extreme heat, we can see variation in the pulse rate. Extreme cold also, we can see variation in the pulse rate. So, and also emotions and also other air quality, or we can say environmental uh, pollutions. So, if I'm not embedding this contextual information, then this is accurately estimated pulse rate cannot be effectively used for diagnostic. So that's called diagnostic accuracy. How to improve the diagnostic accuracy? Even if I'm able to accurately estimate the pulse rate, if we do not embed physical activity informations with that 120 beats per minute, emotion of a person, or the smoking habit, drinking habit of a person, or at the time of delivering, or the environmental pollutions and the weather conditions. Now you can understand, even they say it's a smartwatch and it will display the pulse rate. As an individual, I do not know that this pulse rate is impacted by my activities, or what is called emotion, or the environmental pollutions, because I do not know anything about what is ECG. I don't know any research knowledge. So since I have some research knowledge, I'm able to correlate. If I get the pulse rate 120 beats per minute, I will not have any surprise. I may think that I'm running, I'm getting it. But just imagine the common man who is not having that knowledge. We are expecting that the device should have that knowledge, but the device is not having that intelligent part. But still, we say today AI. So this AI is not adding any kinds of intelligence to improve the diagnostic accuracy of the accurately estimated pulse rate. This is one of the example I explained in terms of the pulse rate. It is applicable for any kinds of health predictions, or we can say health risk predictions, or health, we can say disease detection. We need to embed the contextual information. How do you embed this contextual? Then, since we are going to do any kinds of prediction, or we can say predicting health risk factors, or any kind of diseases, or any kind of life-threatening arrhythmias by using ECG and PPG, we must sense the signal continuously. So when we say the signal is continuously sensed with a higher sampling rate to get all clinical information, that always consumes so much energy. But we are using a limited battery capacity. That means limited battery operated wearable devices, portable devices. So that demands a frequency charging, which it's not possible in some scenarios, and which will be more annoying for an individuals to look for the charging station. So do we have any methods to energize them without intervention of an individual? That's why people work with the energy harvester. But in addition to that, we can reduce the overall energy consumption of this sensing module and processing module and transmission module. We can improve the energy efficiency. That's called how to reduce the energy consumption. That's called improving the battery lifetime, or maximizing the battery lifetime. So in addition to that, when we have efficient techniques to reduce the overall energy consumption, we should also ensure the security aspect when we transmit the data to the cloud for any kinds of predictions. How to ensure the device security? Because the device is connected with the other devices and also a cloud server. So there is a chance for attack. That's called device security settings can be changed by the intruder or enemies. So that will be that can lead to a wrong diagnosis, or that can be a life threatening. That means how to ensure the device security, how to ensure the data security. So now, if you look at all the commercially available devices, sometimes we have to say it's a fancy devices. It can automate the process of accurately estimating all these vital sign parameters under resting conditions. It cannot be used for what is called ambulatory conditions, exercise conditions, if you consider the accuracy and reliability of the parameters. That is a challenge. In addition to that, there is no contextual information are embedded with this type of wristwatches, but still it is purchased and people have used it only just to know what is the reading under resting condition. We should not use under ambulatory and the exercise conditions, because the signals will be highly corrupted with the various kinds of noises and artifacts. So therefore, the accuracy reliability becomes most important research in the domain of health monitoring, that needs a improvement in a diagnostic accuracy, which is called multimodal sensing. Then to do the health predictions, We need to sense the ECG signals, PPG signals continuously, which is called continuous long-term sensing analysis transmission, which consumes more energy and and that demands frequency charging. Then we need to improve the accuracy and robustness of the system under the ambulatory and exercise conditions, because the signals will be corrupted with the various kinds of noises and effects. And timely detection and prediction is most important. Even if I know deep learning networks which can improve the accuracy by 1% and 2%, but it consumes so much energy, it takes some time to give a predicted results. So therefore, the timely detections and detections and predictions is most essential by exploring lightweight signal processing techniques. So in terms of, or we can say, in perspectives of a consumer and user demands, they want a cost-effective device, or we can say affordable devices. So leading to a limited resources. That's very important. Otherwise, if I have 1 lakh rupees, I can buy a wristwatch with a high-speed processor. Then I can buy a battery with a 1 month charging or a 1 year charging. So that cost is very important. So we would like to have cost-effective wearable health devices, and in such a cases, we will have a limited resources. So that limited resources demands the exploration of a lightweight signal processing techniques to accurately and reliably measure all vital signs from the ECG signal, PPG signal, which are sensed under resting, ambulatory, and exercise conditions. So now we must know what are the different kinds of computing architectures that will be used for measuring the vital signs, or that will be used for predicting any kind of diseases or health risk factors. One is called on-device computing. We must know what is the limitations, but we will have a limited resources. Then the edge computing platform, which will have a high-speed processor, but the main challenge is that the cost will be very high. And we should ensure that perfect communications between the sensors and this type of edge computing platform. Similar things applicable for a cloud computing, but cloud computing will have many disadvantages because we must always ensure the communications reliability. You can find there are some locations you will not get a perfect communication. In such a scenarios, how do you transmit the acquired signals to the cloud to get the vital sign parameters? What type of communication protocol that will be used if there is a communication failure? And also we need to ensure the network coverage. If the network is are not available, how do you say that the cloud-based system can predict the health risk factors? So these are the challenges, and there are some advantages in terms of energy, or we can say battery capacity available. Cloud computing means it's always connected with the electricity or power black. We can say that it will have surplus power, but there are many more disadvantages. So now, what is the science in data? Who can be an intelligent data scientist? This is some critical questions we must know, because the data scientist become, or we can say data science become a most popular courses nowadays across the world. But still we do not know what type of science that we want to know from the data. But if you ask anyone, they say that I collected a data, I downloaded a database, I integrated the deep learning. The deep learning gives some accuracy, but they cannot know more than that what they got it. Only accuracy they know. They cannot tell what happened inside also. But still they say we are a data scientist. Now, who can be an intelligent data scientist? That's a big question. That if you really wants to be a good data scientist, we must know what type of sensors that will be used for collecting a signal. Now the question is, why do you want to know sensor? I'm a data scientist. Why do you want to know this sensor? Very interestingly, the sensor will tell what type of information you can get from the signals, what range of information in terms of frequency. I created a model by using a specific type of sensors. Now I'm trying to test that model with the other commercially available sensors for the same application. Let's take microphone. It will have a different frequency responses. And if you take a dry electrodes, if you take a wet electrodes, if you sense the data, what is called on a fingertip, on a wrist, on a chest, on a lower arm, or we can say forearm or upper arm, then or a 12-lead chest, we will have a different kind of clinical information. That means what? A finger tip ECG is used to develop a model, create a model, or to train the model. Now I'm testing with the what is called wrist ECG or forearm ECG. Then obviously I have different kinds of information which cannot be seen, okay, in a fingertip ECG. Or basically you can say these two sensing site will have a different kinds of waveforms, wave shapes, and clinical information. There will be a common information, there will be distinct information which will not be there in one of the places. So therefore, as a data scientist, if I do not know how to create a model by choosing a specific type of sensor, the sensor variation is variability. That's called sensor variability. So in the creation of the model, we must consider the sensor variability. So I'll use wet electrodes, I'll use dry electrodes, I'll use metal electrodes, I'll use capacitive touch electrodes, because each of the electrodes can have different kinds of informations and different kinds of noises and artifacts. So now, if I want to develop a model as a data scientist, I must know what type of electrodes that are used to generate a database which is publicly available. Otherwise, I will be blindly claiming that yes, my model can be used for any kind of electrode. It is not at all possible. I was checking the ChatGPT yesterday. So, what will be the what is called reliability of the system based on AI machines under noisy conditions? It's clearly from the ChatGPT AI tools, we can say that it will not be done because it will create a more false alarms. So therefore, as a data scientist, or if you want to do a what is called any kind of AI-based system, it should be a generic model. Then we must consider all the electrode variability, sensor variability. That's one aspect. Then sensing location variability. Because I developed a model with the fingertip ECG, I can show in some of my research that will have a different kinds of ECG, or we can say local waves shapes. But if I test with the chest ECG electrodes, it will have different. So therefore, for a specific type of diseases or a health monitoring applications, I must consider a sensing site variability also if I want to develop a generalized AI model. Otherwise, everything become a sensor specific AI model and also a sensing site specific AI model. Sensor specific, sensing site specific AI model. Then it will work. Or we can say when you go for testing, I should use a fingertip ECG to get a better result. If I try to use some other upper arm ECG, I can see presence of QRS complex, but I cannot see a prominent sometimes P wave, T wave, or the shape of the T wave, P wave will be different. So therefore, if you look at the 12 lead ECG configuration, or you can say ECG signal, you will find a T wave shapes in a different shapes, different shapes in a different across the channels. Okay, sometimes you will find a 5 basic, sometimes you will find a inverter. So that means you can understand that I need to consider 12 leads. Are we developing a 12 lead based system, or are we developing a single lead sensor specific and sensing site location? So these are the actually science in the data. That's called science in the data. It's not that just downloading the database from the internet and downloading some Python or library or deep learning library, whatever the CNN, LSTM, bidirectional LSTM, or generative model or LLM model. I'll just run it. I get the accuracy. I'll say become a data scientist. You're just integrating. You're getting some result. LLM models also just you are downloading it. So you must know how to create a databases if you want to make a what is called sensor independent model, sensing site independent model. That's one. Then the same type of disease, sometimes we can predict with the multi-model signals. Let's take, we have seen the pulse rate, heart rate. The terms are, one is heart rate from ECG, pulse rate from the PPG. But in a clinically, they proved that both are same. Okay, that is acceptable. Similarly, heart rate variability from the ECG, pulse rate variability from the PPG. That is also well studied. They said that one can replace. Okay, it's a complementary, we can use it as. So now, if I can get some complementary, or you can say some specific information in a PPG, or you can say specific type of diseases can be detected easily by using PPG instead of using ECG that need a electrode placement. So in such a cases, I can say it's called a multimodal signals. I can fuse them. I can improve the diagnostic accuracy also. So that is called multimodal signal. So to understand the function of the heart in general, we use ECG, PPG, and PCG. That's called electrocardiogram, phonocardiogram, and photoplethysmogram. Electrocardiogram is the electrical conduction. Okay, uh, what is called then circulation. That is called PPG, the blood circulation. Then we have mechanical actions. That means we can say heart sound S1, S2, then murmurs. So by collecting or we can say sensing these three signals, we can improve the diagnostic accuracy of cardiovascular disease prediction system. Okay, we may get some features more prominent in this is called multimodal signal. One is called electrical quantity, another is called physical, we can say another physical quantity, and another one is called acoustics, or we can say mechanical quantity. So three different physical variable, or we can say quantity, physical quantities will be used for understanding the normal and abnormal function of the heart. That is called multimodal signal. So when do you use, how do you use, that is called research. Now, can you imagine the so-called data scientists in the world, across the world, or we can say data science is we open in many departments. Are they studying this type of multimodality? What do we use it? And what type of clinical information I can see from a PPG, which can improve the diagnostic accuracy when that cannot be seen in the ECG or in the heart sound. Or we want to understand all the defects of the or all abnormalities of the heart. Few abnormalities can be done effectively with the ECG. Few abnormality predictions can be done with the PPG. Few abnormality predictions can be done with the heart sound. Then that information should be taught for the data scientist, or should any scientist should know, yes, this is the waveform generation from the heart. This is the waveform. This PPG reflects the blood volume flow, and heart sound reflects the mechanical function. That means volume. Murmur is introduced the turbulence of this. So now I can know, yes, this. If I want to understand the defects of the heart wall, I'll give more importance to the heart sound signal. Okay. Then blood pressure estimations, I can use the PPG. So that means that much knowledge, we must know what type of a sensing modality. It's a single or a multimodal. So that's called multimodal, unimodal. Sometimes we use, as an engineer, I know that I'm trying to sense the ECG, PPG signal with a single, we can say reflective mode sensing method with wristwatch. Okay. In the fingertip, you will have, sometimes you will have a reflectance, otherwise you will have a transmittance. Now, it will have a different quality of the signals. The wrist will have, it will have a systolic peak more prominently, but may not have other features more prominent, or you can say it will be masked or distorted due to this low quality of the sensing sensors. Okay, sensors or the locations. Okay, fingertip is more prominent, but wrist is not more prominent to sense the PPG. But if it is only for a pulse rate estimation or to calculate the what is called RR interval or a peak pulse to pulse interval, then I can use the wrist watches. But if I want to do some more diagnostics for by sensing high quality signal, then we have to identify the good location for sensing the PPG signal also. Now we must know this information. Otherwise, we will blindly tell what are the model that I developed by using this database, which is publicly available, useful for any kinds of sensor, useful for any kinds of sensing site. That is not possible. So therefore, we must know. Now coming to this multi-model signal, multi-channel. So I will, instead of using one PPG sensor, I will use 4 PPG sensor with a small spatial distance. Then I will take average of this 4 PPG sensor output. Then I will get a ensembled average. That will also increase the signal to noise ratio. So that is the advantage I can. That's called science in the data. In when there is some prominent noises which have fast varying noise components, which can be smoothed out if I use 4 sensors or 8 sensors or 10 sensors that are placed in a close distance, and if I take an average of 5 sensors or 5 observations that are synchronously sensed, then I will get a very good quality of the PPG signal. So people have attempted, they have developed a 4 LED based PPG sensor. I can say 4 channel PPG. 12 lead, 12 lead ECG we know, 3 lead ECG we know, single lead ECG we know. Similarly, we can see the PPG also. Similarly, we use array of microphone to sense the heart sound. So now this knowledge is most important. If I know this, then I can do some kind of analytics in actual science. I can find interesting insights in the data. Otherwise, I cannot be a good data scientist or I cannot be an intelligent data scientist. Now you know what sensor needs to be used, and we know where what will be the exact sensing site where I can get a prominent feature of specific type of diseases. Then now we must know what will be the sampling rate to collect the signal. Now we must know whether the data science people or yes, data scientists know it or not. Now the question is, they can argue, I don't want to know because I have the data, I have the machine learning, I can get the accuracy. But this is very important. Now I know the specific applications. I'm going to use ECG and PPG for only for this application. Let's understand heart rate variability based sleep apnea detections, or a pulse rate variability based sleep apnea detection, or PPG based, PCG based respiration measurement, or the PPG based blood glucose level monitoring, or the PPG based blood pressure monitoring. Then I must choose a sampling rate in such a way that it can produce a less number of samples without compromising the accuracy of the estimation system. Then I can save the energy of the complete system. That is called knowledge. What will be the suitable sampling rate? That's also research, because every sample process consumes some amount of energy. If I say I sampled a signal with 2000 samples per second, and to estimate the pulse rate, I can do pulse rate with the 25 samples per second. So because I have that knowledge, because my pulse rate frequency is from zero point 0.5 to 5 hertz, I can choose 5 times of this. So that is called a intelligent part of the system when you're designing it. So it's not that model in the what's called database integrity, which called means taking and downloading the database, downloading the Python library, getting some result. But we are trying to reduce the energy consumption without compromising the accuracy. That need what will be the sampling rate that will be used for sensing the data that can reduce the overall energy consumption. Now, in addition to that, in a data questions, we have two important optimal parameters. Okay? Sometimes we can know that quantized weights of the DNN uh, can be with a less model size, and still you will get better accuracy. Similar way, instead of representing each of the samples with a higher number of bits, or you can say 10 bits per sample, I can represent with the 4 bits, 3 bits. Now that can give coarse resolution of the signal. But still, if I can find a suitable techniques with that coarse resolution of the signal, that means 4-bit representation of a 25 hertz sample signal, I can still get the pulse rate. That knowledge is very important. That's called autocorrelation function. So that means what? If I have that knowledge, I can reduce the overall energy consumption, the latency, by choosing a suitable optimal parameters for the data question itself. That means the data question will be a major energy consumption stage because it's going to continuously produce the samples. And it's not a single modality, it's a multi-model, multi-channel, because we want to predict any kind of diseases accurately and reliably. So in such a cases, we must know how to choose the optimal parameters for the data question system. That's called sampling rate and bit. That's called sample resolution. So in addition to that, Nyquist sampling approach to get the digitized signal from the analog sensor, we will also use compressed sensing. It's this is called new data acquisition techniques, which is extensively used in many applications. That's one of the paper I published, parse representations for power quality assessment. Now also we are developing a compressive PQ sensing device. We also develop a compressive ECG sensing device, compressive audio sensing device, because it will produce less number of measurements. With that less number of measurements, I can able to produce a signal, and also by I can measure the pulse rate, I can measure the respiration rate with the suitable sensing matrix. So that's called research. Now, if I do not know what are the different types of approaches that will be used in the data acquisition stage, I cannot able to reduce the energy consumption or even in deep learning networks, because the deep learning networks blindly trained with the 2000 samples per second instead of 25 samples per second. So that means that's called science in data. This is the specific application. If I can play a role in choosing a suitable sampling rate and the bit resolution, okay, then I can reduce the overall energy consumption without compromising the accuracy and reliability of the system. That is called science in data. So that's called data scientist. But unfortunately, without studying this, what is called about the sensor, about the data question modules, we are trying to develop a energy efficient, what is called deep learning based pulse rate estimation system or deep learning based cardiovascular disease prediction system. Yes, there also we can do some kind of energy consumption reductions by exploring a lightweight deep learning model. But there are many stages where we can play a major role in reducing the overall, or we can say reducing the energy consumption of a complete system. Okay, that's very important. So that is called, we can say, uh, selecting a suitable techniques for acquiring a biological signal or biomedical signals. So now, when we collect these signals, we like to transmit to the cloud. So that's why this big Internet of Things become most popular. So we have a Internet of Medical Things architecture, or we can say Internet of Health Things, which try to connect all the medical devices or health devices, which may be a wearable devices, through the internet platform to get various kinds of information. One of the slide I showed, just measuring the pulse rate, that will not be sufficient to do the perfect, or we can say accurate diagnosis. We need a contextual information. Now, if I have some kind of acceleration sensor, gyroscope, some smell sensor with my embedded, with my wearable devices, I can able to get all the contextual information. Or sometimes there are wearables, there are sensors which is installed in my office location, and that can deliver the environmental information to my wristwatch to do this type of diagnosis, or to integrate with my aggregate this environmental information of my office with my health data. Then it will transmit to the cloud by using internet of platform that also improve the diagnostic accuracy. So therefore, the integration of a heterogeneous sensor is most important for improving the diagnostic accuracy with the incorporation of a contextual information. So with to understand what is meant by IoT, it become again fancy words, and everyone is talking about IoT. I developed IoT, but no one is trying to solve the energy efficiency of IoT platform, and no one is trying to solve the that how to develop what is called not only the energy efficiency. When I say IoT based health monitoring system, it's not just integration of all heterogeneous sensors. We have to play a major role. How do you reduce the energy consumption? And why do you want to integrate all such informations? And to understand that, I have taken one example. Yes, you have a smartphone, you have an umbrella as a human, then you have a computer. So they are trying to communicate some informations. So now I can take umbrella as a dead object, but I can put some air quality sensor to sense the environmental conditions. I can put a pulse sensor with this umbrella, I can sense the pulse rate. I can choose air quality and the pulse rate. I can predict what type of problems. That's called diagnostics. Okay, why this pulse rate is very high? Is it due to the pollution, or is it due to the extreme heat, or is it due to the extreme cold? That information I can collect. That means any kind of a data object, if you embed with a sensor, processor, and wireless radio, that become a sensible device. That means it can collect a surrounding information. It's called crowdsourcing. It can communicate or it can share with the other devices to control the function of the other system. That's called Internet of. Without intervention of a human, if I'm able to sense the environment and control the function of the system with the other information or the data comes from the other things. It's called Internet of Things. You are trying to do all control actions based on the parameters sensed and also the decision rules. Okay, that comes from a specific type of sensor. Let's take you have that glucose monitoring sensor, blood, then drug delivery system. They can talk each other, or you have a what is called some kind of a smell sensor. Then you can know what type of disease you can see in future. So that means they are trying to integrate heterogeneous sensors to improve the contextual information. So now, in the Internet of Things, we say information value loop. That's called create, communicate, aggregate, analyze, act. That I explained with a few examples previously. We are using sensors to create it. Then we are communicating. We are aggregating all contextual information to improve the diagnostic accuracy. So now we have this type of framework also that is called Internet of Everything. That's called Internet of Things. Then if you bring the people into that's called people, data, process, things is called Internet of everything. But the challenge is still how to ensure the communication network. Now we must know what are the different kinds of wireless technology that will be used. Now people do some study here also. Yes, I have used this type of wireless technology to transmit my biological signal. And after receiving the biological signal or specific type of wireless radio, uh, uh, can we see any kind of noises due to the wireless channel or wireless disturbances? That also can be done. So therefore, we must know what type of wireless radio that will be used. Then, with reference to the distance, data rate, and power consumption, we like to choose any one of the wireless radio. That's called intelligent system. Now, within IoT, we have different kinds of IoT categories which need to be known because it will give different kinds of challenges. It will address the different kinds of challenges. Trackable object, data object, interactive object, smart object. Now, this is just a variants of various kinds of, or we can say variants of IoT, and one can propose any kinds of IoT architecture, but we have to have own proposed model. That's called IoT model. In this case, I can develop a Internet of Health Things model, Internet of Medical Things model, Internet of Nano Things model, but every model will have different kinds of layers. Now, we know that we use various kinds of sensors to collect a signal. That's called bioacoustic signal. Let us take bioacoustic signal, which can be a stationary, non-stationary, stationary, non-stationary, quasi-stationary, cyclostationary, and monocomponent, multi-component. Now, we must know what are the characteristics of the signal to be processed. We should also know what are the characteristics of the noises and artifacts to be processed. Without knowing, we cannot develop any energy efficient, reliable system. Energy efficient is one of the important, and the reliable system is very important to reduce the false alarms. Now, I must know what is the definition for stationary, non-stationary, quasi-stationary, cyclostationary, monocomponent non-stationary, multi-component non-stationary. Why do you want to know? Now the question is, I'm a data scientist, I don't want to know anything. I have the database, I have the machine learning, I'll just integrate, I'll get accuracy. Yes, we can get, but we cannot make any intelligent and energy efficient. That's why sometimes they say explainability. Instead of that, try to understand the characteristics of the signal to be processed. Then we can be able to choose a suitable signal processing and machine learning techniques. That's very important. If the signal shows cyclostationary, then I can know some interesting characteristic in the Fourier spectrum. If the signal is a monocomponent non-stationary, then I can directly get the instantaneous frequency. If it is a multi-component non-stationary signals, then I cannot get the instantaneous frequency. Then I try to convert this multi-component non-stationary into a monocomponent non-stationary by using some kind of a decomposition techniques. More specifically, we use empirical mode decomposition technique. Now, if it is a quasi-stationary, what will be the characteristics in the Fourier domain or in the time domain? Then we can know whether any kinds of sequential informations that can be captured by the deep learning networks. So therefore, we need to understand the signals characteristics. Most of the people, or we can say in today, nobody is interested to learn what are the characteristics of the signals to be processed. And the noise is most important. Now, in this case, I'm trying to develop I'm trying to develop a cardiovascular uh, disease prediction system, or you can say cardiac arrhythmia classification system. There are variety of arrhythmias we can see. It starts with the arrhythmia means what? Changes in the patterns, or we can say rhythm, irregular rhythm, or we can say in the heart rate, we can say bradycardia, slow heart rate, fast heart rate, normal heart rate. Now, rhythm, that means irregular, regular. Within the irregular, we can have slow, fast, normal. In the irregular, we will have a different kinds of arrhythmias, and the irregular patterns, different kinds of QRS complex, different kinds of P wave, different kinds of T wave. If I do not know this information, one can ask ourselves, how do we create a database, or how do we, or how do you choose the database which is publicly available in the net? That itself a big problem. What type of arrhythmias that we want to solve? Now, if I want to solve a specific arrhythmia, let us take, I want to detect a VTVF, ventricular tachycardia and ventricular fibrillations. Now, if I want to do this VTVF, I must know what is the shape of the waveforms. Otherwise, if I blindly download from the internet, how do you ensure that they will provide a high quality data for public access? The research is also competition. How do you expect it? So sometimes we'll get a noisy data, or we can get some data which is not useful for research study. So therefore, we must have some kind of understanding or knowledge about what is the shape of the signal or the signal characteristics for a specific type of cardiovascular disease, or you can say arrhythmias. So VTVF, you can see this is the actually VF, ventricular fibrillation, looks like this, looks like a sinusoidal waveform. And this is a ventricular tachycardia. It has some good morphology. But if I look at other arrhythmias or normal cases, we cannot find a isoelectric segment. Okay, isoelectric segment. Now, you can see isoelectric segment for a non-VTVF, but we cannot find a isoelectric segment. Okay, with the longer duration, what we can see here for a VTVF. That is of interesting findings in the data. That's called science in data. I'm able to see the what is called, there is no prominent isoelectric segment for a VTVF, but we can see a VTVF for other arrhythmias. That means the isoelectric segment feature itself a distinct feature to discriminate a VTVF from the non-VTVF. This is called knowledge. This is called science in the data. Otherwise, I will collect the data, I will give to the deep learning, it will extract various kinds of features, it will give some accuracy, but still I'm not able to justify whether that result is accurate or not, or acceptable or not. So here I can understand by seeing all kinds of ECG signal with the different arrhythmia, or you can say under the different arrhythmia categories, abnormal ECG signals, normal ECG signals for infant or adult or different age group, different genders, we can easily find the presence of isoelectric segment in most of the cardiac arrhythmias and normal ECG as compared to the VTVF event. That is called science in data. Just imagine anyone, or we can say today generations, or who is talking about data scientist in a public forum, you have to think about it. Do they have such a knowledge that then I can understand, I can use a generative model if I know this is the characteristics of the signal that need to be generated with your GAN network, which cannot be obtained in a practical scenario. That itself a knowledge. If I do not know what I need to generate, or if I think that somebody already developed it, I'm going to use it, there is no research in that way. So therefore, we have to give more importance to understanding the characteristics of each of the ECG signal for a different kinds of arrhythmias. That itself a great research. That is a great science in that. And that means the heart rate patterns are normal, slow, fast, irregular rhythms, regular rhythms, then slope of the ECG, particularly, sorry, shape of the ECG, that will be P wave shape, QRS complex P wave. So sometimes P wave is a tall P wave, basic P wave, wide P wave. If I do not know this information, just imagine how to use a GAN to generate a P waves, which is not can be, which cannot be acquired in a practical cases. So I want a tall P wave, I want a wide P wave, I want a pi basic P wave, I can generate it. But I should know I want. If I want to know, okay, that I need to generate a P wave, so I must understand that what is called the ECG waveform generations methodology, or you can say the various kinds of arithmetic. So the signal processing play a major role in many of the application is called filtering, detection, localization, classifications or recognition, predictions, data reductions, quality assessment, data visualization. Now these are the set of signal processing techniques that's called time domain signal processing techniques, frequency domain signal processing techniques, decomposition signal processing techniques, then instantaneous frequency estimation techniques, then other techniques including singular value decomposition, PCA, ICA, linear prediction. So these are the techniques, signal processing techniques extensively used in the practical applications. So I know from the what is called literature survey or from the textbook, okay, moving average filter, derivative filter, median filter, auto-correlation function, higher order statistics, ensemble averaging, particularly for a frequency domain techniques, frequency selective filters, Fourier transform, short time Fourier transform, or we can say spectrogram. Then we will do signal decompositions, wavelet transform, continuous wavelet transform, discrete wavelet transform, stationary wavelet transform, then empirical discrete wavelet transform, wavelet packet transform, synchronous squeezing wavelet transform, Stockwell's transform, empirical mode decompositions, then median empirical mode decomposition, ensemble empirical mode. So each of these signal decomposition techniques, for each of these signal decomposition techniques, we must find a optimal parameter. We cannot escape from finding the optimal parameters for each of the signals. Sometimes I just want to use a wavelet transform. Then sometimes we say that the frequency selective filter is required, selection of the bandwidth cutoff frequencies. Okay, that may not be required in a wavelet transform. But still, in the wavelet transform, we need to choose the mother wave. We need to know what type of which subband will be used for specific type of noise removal or to extract the QRS complex. That is also optimal parameter. So that means what we cannot escape from finding the optimal parameters of your decomposition. So that means each of the signal decomposition techniques has their own advantages and disadvantages or limitation. We must understand first. We should not blindly use wavelet transform for analysis of the symbol, what is say, some harmonics, or you can say some what is say, signal with the localized frequency component. It's good for a transient analysis. So we must know when to use, how to use, where to use. If sometimes we blindly use it, then we'll criticize that is not giving good result. That's itself wrong. We must know Fourier series used for specific application, wavelet transform used for specific application, then empirical used for specific application. But still, in empirical mode decomposition, the purpose is converting a multi-component non-stationary into a monocomponent non-stationary. It will produce many oscillatory functions. That's called IMF, intrinsic mode functions. Now, if you get 10 intrinsic mode function, I do not know which mode functions will reflect the QRS complex, which mode functions will reflect the P wave and the T wave, but that can be easily obtained from wavelet transform because each subband will give the frequency range. But selection of the mother wavelet is very important. But in the empirical mode decomposition, it's a data-driven decomposition techniques, but we must know which IMF that needed further analysis. So that is the limitation of EMD as compared to the wavelet transform. The advantage of wavelet transform is I know what is the frequency range of each of the subband, but that information cannot be obtained in the EMD. So now this is called analysis. As an engineer, you must know that how to use, when to use, based on their what is called pros and cons. That's very important. The wavelet transform is defined for only transient analysis. We should stick with that one. But if I want to do some kind of multi-component to monocomponent, I can use wavelet transform. I can use empirical, but empirical will be more appropriate to get the oscillating function. But the problem is that I will not get the bandwidth because empirical will have advantage of what is called data-driven techniques. That means there is no need to need to know how to choose a mother wavelet in the case of a wavelet transform limitation. So that's why that is summarized here. That means we cannot escape from finding the design parameters, including moving average filter or median filter. What is the filter length? Transform domain techniques, what will be the noise threshold? In a filter band techniques, what is the cutoff frequency? In wavelet transform, selection of the mother wavelet, selection of the characteristic subbands for the signal to be processed or signal to be removed. And then empirical wavelet transform, again, this is the issue. Then we have variation mode decomposition, then sparse signal decomposition. And then, if you know how to choose the optimal parameters for your specific application, you should choose a lightweight decomposition technique. Therefore, the computational complexity and power consumption become the innovative metrics. Today, we want to reduce the latency and reduce the energy consumption because we implement all this what is called predictions, detections, and classification algorithms on a resource constraint platform. Particularly, it has a limited battery capacity. So therefore, we need to reduce the overall energy consumption by exploring suitable, or we can say lightweight signal processing techniques, or particularly signal decomposition techniques. It should be practically realizable. That's also most important. So these are the main important points that we need to consider when you try to choose any kinds of signal decomposition techniques. Now, coming to artificial intelligence, again, it's become what is called one other fancy words, but you can find everywhere. People are talking about artificial intelligence. But if you really check with the AI tools themselves, they say that I cannot produce a good accuracy for the noisy data because I'm not able to get any kind of insight from that. That is the limitation. That is not at all possible. So therefore, checking the quality of the signal, either by using deep learning networks for signal processing technique, is most important. So even today, yesterday I was checking with the AI platform. It's clearly mentioned that we cannot what is called produce a high accuracy or reliable answers or outcomes for a severely corrupted ECG signal, PPG signal, which can be encountered in a practical daily ambulatory and exercise conditions. That's the biggest problem. But it can automate, it can give accurate, but still you can use your deep learning architectures, or you can say AI architectures, to what is called check the quality of the signal, or you can use traditional signal processing techniques to check the quality of the signal. But that depends upon the computational complexity, or you can say computational resource constraint. So again, at least we must know what are the different types of AI, and we have artificial narrow intelligence, artificial general intelligence, artificial super intelligence. But today we are imagining everything is artificial super intelligence, but most of the commercial product which is available in market is only artificial narrow intelligence. Even that is not intelligence. It is just a process improving the accuracy of the estimation by using deep learning network. But intelligence is beyond that. Whether the pulse rate can be useful for medical grade or not, that depends upon the conduction. So that's why we must know this chart that is called, something is called retrieving responses, generating responses. That the questions comes from the closed domain and open domain. So if you come to open domain in a generative responses, it's called generative AI. It's the hardest to achieve. Then there is something is called retrieving responses in open domain, impossible. Then intelligent machines are to achieve, then that is called generative. So we can understand there are a number of problems when you come to the critical engineering, so our critical applications. But if you think about the generation of the movie, generation of the photos, generation of any kind of a robotic system with a limited number of rules, even 1,000 rules, 10,000 rules, which are limited, it is well defined. Then therefore we are able to get good accuracies, any kind of automation, particular robotic system, or you can say drones. But when you consider the environment with a different noisy condition, then most of the system fails, including AI platform. So now when you collect the data, what you want to do with the data, we are trying to do some kind of analytics. That's it. It's called, sometimes we can say data analytics, big data analytics. Now they are saying a data scientist. So only the titles, fancies become changing, industry-driven research, and academicians also changing the title. But basically, the data analytics includes descriptive analytics, diagnostic analytics, predictive analytics, prescriptive analytics. If I know all four data analytics in detail, in particularly understanding the concept and what we need to know from this each of these analytics, then we can solve this problem. Particularly, descriptive analytics aims to answer the question, what happened? So I got a what is called pulse rate of 120 beats per minute. So that means something happened to my heart. That's all what happened to my heart in a given period of time, 120 beats per minute. Now that 120 beats per minute, to get that 120 beats per minute accurately, I will use specific type of data if I'm using the deep learning network, or I can use specific type of signal processing, and I'm able to more accurate. I am able to get a pulse rate accurately and reliably. I'm able to tell something happened to my heart because my heart rate is pulse rate is 120 beats per minute. But the diagnostic analytics says helps answer the questions more on why something happened, why this 120 beats per minute. Now you understand from my previous explanation that yes, this pulse rate can be defects of the heart functioning, or the pulse rate is because of the emotion, or the pulse rate is because of the running, or the pulse rate is extreme heat or extreme cold. Now that is called additional information that need to be integrated with your wristwatch or wearable devices. Then we can tell that pulse rate can be effectively used for diagnosis purpose. That's called diagnostic analytics. When you come to the diagnostic analytics, I need additional information to do diagnosis the accurately estimated pulse rate readings. That has a different challenging problem that demands different computing platform. So that means finding more descriptive analytics and deeper to find your causes. Why this happened that 120 I got it because of this reason, but that needs additional contextual information, that need a different computing platform, that need a different machine learning techniques. That's why I said we should know the meaning of the diagnostic analytics. Then you are expert in data science because this will decide what type of machine learning tools need to be used, how to collect those informations. Okay, without those information, I cannot do any kind of diagnosis of the pulse rate. Now, predictive, that means what help to answer questions about what will happen in the future. Yes, let us assume that my 120 beats per minute is because of the heart functioning. If that is detected and that is known that yes, this 120 beats per minute is because of the heart malfunctioning. Now, what I have to do? That's called prediction. The prediction needs a history. What is the history of the person? Now, he got a 120 beats per minute. Is it athlete's person or it is a normal subject? Let's take, I got a 40 beats per minute. Sometimes 40 beats per minute is, if for athlete, it's a normal, but in the cases, it becomes what a bradycardia for a non-athletes or not a regular athletes. Then that means we should know this history of that person. Now, collecting a history information becomes challenging. Now, that the history needs to be fused with the different kinds of machine learning. So that demands a different kinds of machine learning techniques, computational platform, data. That's called predictive analytics. Now we are going to the prescriptive analytics that help answer questions about course of action. Okay, this has happened, and you are athlete. Then you have to do this type of what is called. You have to go for this type of treatment process or kind of we can say uh, monitoring process. That means that's called prescriptive. That means a different kinds of signal processing, machine learning, history. So then you can understand the meaning, and also to know the key challenges that need to be addressed. Otherwise, one cannot simply tell I'm developing what is called a system which can do descriptive, diagnostic, predictive, prescriptive. We can develop, but we need so much knowledge, so much data. So instead of that, as a research student, I can tell I'm going to work with only diagnostic aspect of it. Then I will do this. I assume that pulse rate is accurately estimated. From there, I will start. I will tell to diagnose this pulse rate. These informations are important. I am going to develop a sensor. I am going to integrate them. I am going to do effective diagnosis of the pulse rate. That is accurately estimated. No, I am not going to work with the diagnostic analytics. I am going to work with the descriptive analytics. I will focus with the what is called lightweight signal processing or a deep learning model to accurately estimate the pulse rate, whether it's what is called due to the tachycardia, due to the heart defects, or due to the emotions, or due to the physical activity. I don't mind, but I want to accurately estimate the pulse. So therefore, we must know the meaning of the technologies that itself gives what are the key challenges that need to be addressed, and what are the signal processing, image processing, or we can say machine learning techniques that need to be used. So I'll just cover that yes, energy consumption is most important. So I can reduce the energy consumption by exploring suitable sensor integration, and then data questions, signal analysis, data transmission, and storage levels. Now, if coming to the title of the talk is a quality aware. Now, when I use this type of sensors, we will get a noisy data. So we will get the yeah, we will get a noisy data. That means what? My ECG signal under ambulatory conditions will be disturbed with the motion artifacts due to the movement of the electrodes or the sensors, or it can be corrupted with the muscle artifacts. So these muscle artifacts and motion artifacts, as an electronics engineer, I know that it has a bandwidth which is overlapping with the spectrum of the ECG signal. But I do not know whether the data scientists know it or not. But everyone should know what is signal, what is sensor, okay, what are the noises, artifacts that I can see from ECG recordings. Then I can develop an intelligent deep learning network or intelligent, still I can say intelligent AI model because you should know that this signal is corrupted with the noise. I am going to produce a false alarm, which is more annoying, which leads to wrong diagnosis. Therefore, I will not process by detecting the presence of the noises. That's called intelligent part of the system. That is the main research work that we do in our research lab. That is called checking the quality of the signal. It's called the biomedical signal quality assessment. Particularly, it is called biosignal quality assessment for ECG. So here you can find the ECG, normal ECG. That means a clean ECG, or you can say noise-free ECG. And this is the ECG signal corrupted with the electrode movement artifacts. When I take a derivative, and we can see that the noises were emphasized. Now, in this case, this is also a ECG corrupted the muscle artifacts when I take the derivative this. But why do you want to do this derivative analysis? Because most of the practical application of ECG and PPG analysis, they use the first order derivative to get the prominent feature information. So therefore, if I get a noisy derivative waveforms, then I'm going to get a unreliable crucial points or parameter points. Okay, that will be challenging to accurately get the important crucial points from the original ECG and PPG signal. So therefore, we need to check the quality of the signal in a raw domain also, or you can say in original domain and also in a derivative domain, because the derivative of the ECG and PPG waveforms are extensively used to locate the other fiducial points and also to get some more clinical information. So therefore, we have taken the derivative to demonstrate that yes, it's a more prominent in the derivative domain. So, and here if you see, we have a ECG signal which is corrupted with the muscle artifacts for a small portions. So instead of completely discarding, its entire signal is distorted. I can completely remove from the further analysis. But in this case, only portion of the ECG is disturbed, or we can say distorted. So I'll try to develop a techniques where we can say which can locate the disturbed portions, or we can say find the start and the end point of the noisy portions. Then we'll remove only that noise portion, or I will process this noise portions by using denoising techniques. So that is called innovations here. So that means I'm not going to discard the entire ECG signal. We are going to find a start and end point of the noisy portions. Then we will discard or we will process by using denoising technique. That is called what is called ECG signal quality assessment. It's a process of detecting the what is called presence of the noises and locating the noisy portions and classifying the type of noise. That's very important. That's called intelligent. For example, when we say my signal is corrupted with the muscle artifacts, then I'll use a specific type of signal processing techniques to handle the muscle artifact. If it is corrupted with the baseline model, I'll use a different kinds of uh, signal processing techniques. If it is a corrupted with the power line interference, I'll use some other signal processing techniques. Now, by using a noise-specific signal processing techniques, I can remove the noises effectively. I can also tell what type of waveforms will be distorted because I know this signal processing distort this type of information in the signal. Let's take a DCT based sometimes noise elimination. The DCT based techniques can distort the QRS complex. Okay, even a Fourier transform based techniques. So now I know that if I use a DCT compression or a denoising techniques, then we can tell that since this is processed by using DCT, I can expect the distortion of the QRS complex. Then when I'm using the decompressed version of a signal by using DCT, I must be careful in using the QRS complex because this cannot reproduce the QRS complex. Okay. So that's why you can say noise-specific signal processing or denoising techniques more effective in highlighting what type of distortion that can be seen in the reconstructed signal, and also that it can reduce the overall computational load and that can remove the noises effectively. So that is called what is called innovations. Okay, so that's the one we studied, and we demonstrated here. Many have explored the deep learning architectures to measure the pulse rate from the noisy PPG that comes from the wristwatches. So here, if you look at this table, you can find the mean absolute error of 19 beats per minute, 20 beats per minute, 10 beats per minute. But there are some techniques they showed one, but that are actually, frankly speaking, those techniques are not validated properly, and we cannot get it. Somewhat they taken, but the measurement is also wrong. So now, if you see most of the techniques, it shows a higher mean absolute error for a wrist PPG. That itself a very challenge. So here we are saying that instead of using a computationally expensive techniques to estimate the pulse rate, still that results in a larger error. We can simply throw because it's going to uh, affect the reliability of the system, or it's going to produce a wrong diagnosis. So therefore, we check the quality of the signal, because beyond some level of the noises, we cannot completely remove the what is called noises and artifacts from the signal without it distorting the local waves because of the in-band noise character, or we can say overlapping. This is called knowledge. We do not know how many of you know in-band noise, out-of-band, which having overlapping spectrum. Is it possible to accurately? What level of muscle artifacts I can accurately use QRS complex? If it is accurate, if the muscle artifacts level is more than 70% of the QRS, sometimes it's very difficult to detect that or locate the QRS complex itself. That's severely corrupted signal with the muscle artifact. So that is why we check the quality of the signal. We discard from the further processing. So all these algorithms that we implemented, this is the PPG signal that we implemented on Arduino. Here we implemented, we also induced by moving the hand, we introduced the artifacts, then we are our algorithm, this is the orange color, able to detect the artifacts, and this is the good quality portions. Then we can use this good quality for estimating the pulse rate, and further processing. We discard this bad quality from the further processing. Then we also calculated other PPG parameters, which is called pulse rate, crust time, decay time, then pulse, we can say PPG intensity, that's called, this is called PPI, that is called pulse to pulse interval. This is foot to foot interval. Then this is pulse intensity ratio. This is called systolic slope. This is called systolic height. This is pulse width area. So we are able to get all the parameters from the PPG on Arduino itself. That is called innovation. That means instead of looking for a deep learning to do all this job, if that can be done with the classical signal processing techniques, you can imagine how much energy consumption that can be reduced, and also it become a low cost solution. And that's the one we demonstrated, that for a case one, completely noise free, the extra energy consumption is 4.36. And for a case two, completely noisy, the saving energy is 95%. For a case three, 5% is the noisy, then the saving is 8.33. But one can argue, if I get a noise-free signal 24 hours, I'm going to consume this much energy. But frankly speaking, under ambulatory conditions or exercise conditions, you will have minimum of 4 hours, 5 hours of noisy data, which will not be useful for any clinical studies. Because maybe you will get pulse rate, but rest of the parameters will be completely distorted. And even AI cannot do, that is a what is called output of the AI search engine. So I checked, it clearly says that classical signal processing can do better than this AI model, because they cannot able to still get the information if it's corrupted with the noises. So therefore, this study will be very much useful for ambulatory, where we have more than 4 hours of noisy data, which can save that much energy, bandwidth, because we made a quality of our communication protocol, quality of our PPG processing protocol, because once you check the quality, then we'll do transmission and processing. So we also explore the integrated data compression pulse rate. This is very interesting techniques which we studied in a classroom. Sometimes we have to reinvent what we studied in the classroom. This is called a differential pulse code modulation, which produces the quantization that we can say residual error. If you see the third waveform here, it's a quantized residual error from the DBCM, which will be transmitted. Then I can get back the original from the residual with a predictive coefficient. That's called DBCM. Now we processed this quantized DBCM by using filter, then we are able to get these parameters. So you can see that's called integrated data compression and pulse check. Is it audible what I'm speaking? Hello?
Yes, sir.
Yes.
Yes, sir. Clearly
Okay.
audible.
So in the third important application of the quality checking protocol is that when we sense a signal, if that signal is connected to the noises and artifacts, we will not have good redundancy among the samples. So even if we use wavelet transform, discrete cosine transform to compress the noisy signal, we may spend more number of bits to represent a signal if I develop a quality control data compression techniques. In such a cases, it needs more bit. That means I cannot get a compression efficiency. That was demonstrated here. That means compressing a noisy signal, we cannot get a good compression efficiency. So that we proved it, and then this also published in IEEE. That means, so if you check the quality of the signal, if it's a bad quality, we should not try to implement a quality control data compression, because it will demands more what is called bits, because to represent a noisy also need a more bit, because it's a quality control based data. Then that also we developed with Arduino, which was published in IEEE. Then we developed a PPG based pulse rate and respiration rate measurement system. That's also we implemented on Arduino. And then this is very interesting, which I presented in one of the slides. If I can understand the characteristics of the signal, I can still develop a classical signal processing technique based cardiac arrhythmia, or you can say life-threatening arrhythmia detection, instead of using a CNN-based architecture or deep learning network. Now, when I say that I'm going to use classical signal processing, very difficult to publish nowadays, because they expect that everything should be done today is deep learning. If you use classical signal processing, still if you get accuracy, it's difficult to publish. That's unfortunate things happening here. So, but in such a cases, you try to compare both the techniques. That means one is classical signal processing techniques based on your observations on the signal characteristics, and then deep learning architectures, which is extensively used nowadays, which consumes more energy, which demands more model size. Okay, it will use more number of parameters to detect this type of events. So what we seen here, from A to H, and we from A to A to E, you can find isoelectric segment, and then from F to H, it's called ventricular tachycardia, ventricular tachycardia, ventricular. So we simply applied a number of zero crossings per segment. For this given segment, we calculate the number of zero crossing. I consider all kinds of arrhythmias by using MIT arrhythmia database, and you can find that there is no much in this what is called clustered formulations between the non-VTVF and VTVF, because it's completely overlapping. It is difficult to discriminate them. Then what we did, that since it is having isoelectric segment, we injected a bipolar sequence, and then we can find that ECG signal with the isoelectric segment will have more zero crossing rate or number of zero crossing per segment as compared to this VTVF. Therefore, it forms the what is called two clusters. This is called VTVF clusters. This is called non-VTVF clusters, which includes all other cardiac arrhythmias. And then this what is called feature visualization, or you can say scatter plot, based on the real-time data, which is from the MIT arrhythmia database. We consider all arrhythmias. You can see this side legends. So now with this, we can conclude simple zero crossing rate is sufficient after adding some alternate signs change to this. Is called innovation. Okay, I can do this task, VTVF detection task, by using only zero crossing rate with the intelligent of isoelectric segment, which was observed with 6-month experiences. Okay, now I need to demonstrate will it be more effective or not. So we'll also develop a CNN based techniques. Instead of blindly using CNN to do the VTVF detection, we used to filter CNN, unfiltered CNN. In the sense, I used pre-processing and particularly bandpass filter to remove the noises and artifacts beyond some frequency range. Let's take, I studied with 0.5 hertz to 40 hertz. The remaining 40 to the FS by 2 noisy components, or we can say unwanted components. So we found that the filtering based CNN even the that will gives better accuracy than unfiltered signal. That's a we can see the blue color is original, it's unfiltered, and this is the filtered signal. We can see the improvement in the accuracy of a filtered CNN in detecting the VTVF. Then we compared with a different block length for a CNN with filtering, without filtering. So we can see the improvement in the accuracy. Sensitivity is 94, here 97, but here is only 89, here 87, here 91 with filtering. That means still signal processing can serve as a what is called pre-processing. That is the actual information I got from ChatGPT also when I checked with the checked for reliability and accuracy under noisy. It's recommended if we can use a classical signal processing to filter out, because sometimes we are confusing the deep learning also to giving a so much variations in the noisy data, which are out of band noises, which can be eliminated. Why do you confuse them? That is a very clearly we can see that the ECG signal spectrum is within this range. So why do you want to cover all other ranges by fs by 2? May not be required from that 40 to fs by 2. So that was our observation and contribution. We found that with filter based techniques was good. Then we finally compared with the zero crossing based method and with the CNN. We found that zero crossing based single feature based method provides a promising results than the CNN, which has the millions of parameters, which consumes more energy. Particularly, VTVF will be embedded with the external defibrillator, which is an electric shock provider, which will be battery operated. If that battery's capacity or energy is used for what is called detecting by using CNN, which are millions of parameter, then if I use only it's called zero crossing rate, then I can save so much energy, which can use that one-time charged external defibrillator for long-term monitoring. So that was our innovation. That is the work I demonstrated here. So that's why I say that is called what is science in the data. Who can be an intelligent data scientist? I do not know how many scientists they know that VTVF has this interesting characteristic. We think that I will collect the data, but first of all, who will provide VTVF data and from the hospital, and for all variants of VTVF, non-VTVF, who will provide, and how do you train them to have all variety of sensor characteristics, or we can say sensing site and a different gender age group. But isoelectric segment is exist in all the cases. So therefore, we say that sometimes the science in data, in the sense you should know, or we should know the knowledge more about signal characteristics and noises artifacts to be deemed or to be processed. So with this, this is the very final conclusion that sometimes we use physiological signals for diagnostic purpose. Sometimes we use same ECG for PPG for a physical activity. I have seen same ECG people have used for emotion recognition. Same ECG and PPG they used for biometric. But when I want to do diagnostics, I must provide what is called physical activity. I must provide human emotion. I must provide your. So when I want to do physical activity, I should tell that he is a normal patient. When I want to do biometric recognition, I should have a normal patient, and also I should have a chronic patient. So that means this is the biggest confusion block in the world, that yes, sometimes we do some research, but you can see we have to fuse all four, what is called 5 blocks. If I want to have a reliable diagnostic accuracy, reliable physical activity, fitness monitoring, or reliable emotion recognition, or reliable what is called biometric recognition. So with this, I'll conclude my presentation. I'll just open for the discussion. Thank you for listening my talk.
Thank you, sir. So, the few participants have some questions, sir.
Yes.
Arya Mehta, Dr. Arya Mehta.
Yeah, good morning, sir. Hello.
Yes. Yeah. Good morning.
Yeah. Sir, I just want, I used to use this ECG as a reference ground truth. So many
ECG.
data sets, ECG. So many data sets have to have a very noisy sort of that thing. Like only R wave is visible. Rest of that is already covered in noise. And in many cases, even R wave is not properly visible. So in that sort of thing, how we can utilize that reference ground truth for like doing all those
So
things.
if for example, if I take any ECG from a specific data, you can say database or a data set publicly available, they give ground truth